So as I mentioned this week, packets for all the material on vectors. You do not need your regular book. So if you're looking at the homework, make sure you look in the packet. All right, so since some people have already studied a little bit about vectors rather than just give you everything, I'll ask you a couple of questions and see what you know or what you don't know. So a vector is generally used to represent two things at the same time. What is a vector used to represent?
Magnitude and direction.
Yep. So it's a quantity that has magnitude and direction. The two examples that we're really going to look at of vectors in this class are velocity vectors. So a velocity vector, Matt, are you all set? Thank you. A velocity vector represents the speed of an object traveling in a certain direction. So we'll look at an example of that with airplanes in a second. But for any airplane that's flying right now, if you want to describe how it's traveling, you have to describe two things. What's its heading, what's the direction, and how fast is it going? That's its magnitude. Another example you can use vectors for, you probably did that in physics, is force. So with force, the magnitude would be how hard you're pushing or pulling, whatever kind of force you're exerting on something. And the direction is which way you're pushing. So there's a difference between me pushing down on this table with 50 pounds of force or pulling up on the table with 50 pounds of force. Okay, it's different direction. All right, so here's an example I was mentioning earlier with the airplanes. So you can think of all these planes as vectors, and they all have different directions and speeds. Now, normally we use an arrow to represent a vector. Okay, so you can kind of think of these planes as arrows. The direction that the arrow points, well, that's the direction. But if I wanted to show you a bigger magnitude vector versus a smaller magnitude vector, how would that change my arrow? If a vector has a bigger magnitude, then the arrow would be, what do you think? How would you draw it? Yeah, it would be longer. Okay, so with the length of the arrow, that's the magnitude. And the direction the arrowhead points, well, there's your direction. Now, when I bring the example with the planes back up, the planes don't have different lengths. Each image of the little plane on the screen, they're pretty much the same size. I think they have different images for the type of aircraft, but some aircrafts, but they're not different size airplanes. Okay. Another thing that makes this a little bit more complicated is you have to visualize it in 3D. It might look like certain planes are really close, but one could be on the ground, one could be at 30,000 feet. Okay, it could be different altitudes. Let's click on this one. So this plane over here looks like it's heading east. Okay, when we deal with direction, okay, they describe it as a compass heading. East would be a heading of 90 degrees. That's not how we do it in pre-cal. East is usually 0, but on a compass, east is 90. So if I click on that plane, we'll see its flight path. And we can see that it's pretty much been heading east. Took a little bit of a turn, and there might even be some small turns in there we can't see. But overall, the direction is east. Okay, on a plane, they call that the route. Now, the route here is described as a bunch of letters and numbers. To a computer, those letters and numbers mean something. Maybe even a person that knows how to read it. But we can click decode, and it explains for us the route. And if you look at the headings, 80, 90, 90, 100, 100, 90, those are all pretty much in an east direction. Okay? And it shows you what device is measuring that, whether it's an airport or maybe some kind of buoy or marker that's measuring the direction. But that's the point. It has a direction. And the speed, I don't know if we can see the speed. Did it have speed? Yeah, speed, 598 miles an hour. So that's how fast it's going. which means it's probably flying with the wind, because a lot of times planes don't, 600 miles an hour, it's pretty fast for, I don't know what kind of plane it is, but a passenger plane.
That's the ground speed of it.
Yeah, that's
when it's going through the air is pushing from behind, it doesn't actually be going through this air that fast.
Yeah, and we're going
to... The speed is going over the ground.
The speed over the ground, so like if you pointed a radar gun at it from the ground, I guess that's how fast.
Yeah, like if you're flying into the wind, it'll say you could be going like 100 miles an hour, but you're actually moving over the ground at 0 miles an hour because the wind's like coming at you at 100 miles an hour.
It's like you're just staying still.
Yeah.
And we're going to talk a little bit about that. We're going to do a problem where a plane is flying, say north, and it's got a wind blowing northeast, and I want to know what would happen. Would the plane go faster? Would it go slower? And what would be the new course? If you didn't adjust anything, how far off track would the plane be blown? So do you fly? You fly planes, right? Yeah, that's cool. So here you can also see altitude. We don't really get into the 3D part of it, but you could get into 3D. And each airport, you can see if I zoom out a little bit. Actually, the airports, they're pretty easy to tell because the traffic looks very congested around them. So definitely an airport in there, maybe JFK, I can't quite tell. Buffalo is out there, DC, down in there, Logan. Yeah, so there's a ton of planes. Okay, I don't know, thousands of planes.
Those are all flying?
Yeah, they're all flying. There might even be more.
The green ones are flying right now, right?
The green ones?
Yeah,
The green ones are just airports.
Or something.
The green ones are just...
Those dots are just airports.
They look like planes from here.
Yeah.
Can't really tell. How do they not cross paths? Yeah, how do they not hit each other?
Well, that's the job of the air traffic controller, to make sure they maintain a distance between each plane. So there's a certain safety margin I'm sure they keep between every plane that's coming in for a landing.
Could you ever pass like one? Do you think like it could be in like the same lane?
Probably not
Not
that
the
close.
same one, but
You might see one.
That'd be so
When
sick.
I was in Florida, there was a plane probably like a mile away from, not even a mile, like half
Did
a
you
mile
see it?
away. Yeah, you could see it. It was so close. It was
Did you
so
see the
weird.
equal point?
No, but it was creepy. I was like, what the?
Yeah, so it's the job of the airport to kind of coordinate that traffic that's coming in and make sure that planes are keeping the same distance.
That's why we're in the sky. Like,
Yeah.
stretching and going down. We're just chilling in the sky.
I don't know, that seems close. It's a
It
little
was
close.
creepy.
Alright, so let's take a look at the next part. When we're representing a vector, whether it's velocity or force, we can represent it basically with 2 points. Where the vector starts and where it stops. Where it starts is called the initial point. Where it stops is the terminal point. And it's important we get those in the right order. If you switch them, then you're going to switch the direction. So in geometry, a lot of times we call that a ray. So you could use the same notation here, call this ray PQ. Or in trig, we have another way to represent it using a single letter. Now the problem with using a single letter is we already use letters in trig, or anything else in math. Letters are variables. So if we're going to use a letter to represent a vector, we've got to make it a little different. There's 2 ways you can make the letter different. You can write a letter with an arrow above it. This arrow above it does not have anything to do with direction. This is just a symbol, meaning if you put an arrow pointing to the right above a letter, that letter is a vector. So this is vector M, or you can make it bold. If you look at the packet I just gave you, they do it the second way. They make it bold. Okay, so any questions on the 2 ways you can write a vector? All right. Okay, first thing we're going to look at is adding 2 vectors together. And if you're trying to think, well, what's an example where you could add two vectors together? Think of, let's go back to the airplane. Think of an airplane flying east. And then let's say there was a wind blowing to the east. Well, what would happen there is if the plane is flying like 400 miles an hour and the wind is blowing 50 miles an hour, that's a tailwind, it's going to push the plane. So what's going to happen? The plane's going to travel at a different speed. It's going to be a combination of how fast the engine is pushing the plane and the wind behind it. All right? Same thing with force. If I push on a table, let's say I push on the table kind of towards you guys at an angle, it's going to go kind of towards you and towards the wall because I pushed at an angle. And then if somebody else was pushing at the same angle, well, kind of like on the other side, we're kind of fighting each other. So what might happen is if you're pushing forward and to the right and I'm pushing forward and to the left, the table might end up moving forward, but we're also kind of fighting each other the way we're pushing it, because you're kind of pushing right and I'm pushing left a little bit. But the idea is when we each push, there's a new force on the table, a combined force of both of us pushing together. So the idea is when you add two vectors together, you get a new vector. Okay, so two forces acting on the same object, you have a new magnitude and you have a new direction for that force. And we'll look at more about finding the magnitude and direction of combining forces numerically. We'll do that tomorrow. We could do the problem with the airplane, or we could do the problem with the boat. It's pretty much the same thing. Whether you have an airplane and the wind is blowing it, or you have a boat and the current is taking it. It's the same idea. Okay, so I'm going to show you visually how we add two vectors. Okay. Has anybody added vectors visually before? No numbers at all. Just a visual. Okay. So the way you add visually is, let's say the black arrow is vector v, and the red one is vector w. If you want to do v plus w, you line the vectors up just like that. Okay, I'm going to write it all out, but the idea is you connect the end of one to the beginning of the other. And the final answer would be that. That arrow that I just drew in green, and I just moved it off to the side so you could see it, represents this plus that. So notice that the answer is a new vector. It's an arrow. It has a different length than each of the originals, so a different magnitude, and it's pointing in a different direction than either of the original ones. Okay, so let me explain what I just did. So to add v and w, you have to line them up. So the ending point of the first one is right on top of the starting point of the second one. That's the first part. The second part is then to draw the final answer. That's what's in green. So to get the final answer, take where you start and draw an arrow to where you stop. So for these kinds of problems, the answer is purely a drawing. Yeah, no numbers. And drawing is okay. At least we're going to start out practicing with drawing. And drawing is still good for a word problem because it's always good to visualize when you have a word problem. But in general, if you just had two vectors and you want to add them up, we want to learn how to do it with numbers. Okay? We don't want to have to make a sketch every single time for everything we do with vectors. Sketching is time consuming. Okay. Any questions on what we did there? So that represents V plus W. If I wanted to do W plus V, we do it like that. But we'll look at that in a minute and see, is there any difference? You take V plus W or W plus V, do you get a different answer? I'll show you that in a second. Okay, so let's add V plus W. One disadvantage of doing it graphically is you kind of have to plan ahead. I see that V is down and to the right. I see W is to the right. So I'm going to be doing a lot of movement right. I don't want to start on the right edge of my graph paper. I'm going to run out of space. So keep it towards the left and probably a little bit up because you know you're going to go down. So there's V, take W, put it on the end, and now connect where we started to where we finished. Now you can leave the answer right there, that's fine, or I'm just going to move it off so you can see it clearly. That's the answer. Again, pretend if you don't see a letter that's bold, I try to make them look bold, but it kind of takes forever to make every letter bold. Just know that letters should be bolded today. Okay. Any questions on how we just added V plus W? Right, so you can kind of think of that, pretend that first arrow right there is a plane. That vector right there represents wind. If that plane was flying, the wind is going to push the plane along and it's going to go faster. How do I know? Look at the red arrow. It's longer. It's going to mean it's going faster. And the plane is going to go a little bit more to the right than it is down. So you can see the angle. If the plane intended to fly in the direction of the black arrow, it's going to be blown off course a little bit. So the pilot would have to correct for that. Okay, let's try this one. What's going to happen here when I add these up? They're going to cancel out because what's the same about those vectors? Their length, their magnitude. What's different? Direction, and the direction is exactly 180 degrees off. So, just to kind of go through it, even though we know what'll happen, you're going to connect the terminal point of V to the initial point of W. You're going to line up those red dots. Then after you line them up, connect the start of V to the end of W. So after we line up the red dots, then connect the green dots. But, as you guys already said, when you line up the red dots, the green dots also line up, so there's nothing to connect. So, we get that, the zero vector. Or you could write it this way. When you add two vectors, you always get a vector. You don't get a number. So you can't write the number 0. But what you can write is the zero vector. The zero vector is kind of weird. It's an exception. I said to you that all vectors have a magnitude and a direction. Well, the zero vector doesn't. You can almost think of the zero vector, it's like a point. It doesn't have any length. It doesn't point in any direction. So don't think about it too much, but it's just kind of an exception. Okay. Any questions on that? All right. So now we're going to get into a couple of properties with vectors. One thing that you can't do is you can't assume that anything you know right now about numbers applies to vectors. You can't. You know that when you add a number to a number, you can do it in any order you want. 2 plus 5 is the same as 5 plus 2. Well, we can't assume that that works with vectors. I will tell you it does. But there are some things that you know right now about numbers that will not work with vectors. For example, multiplication. If you multiply 2 times 3 or 3 times 2, is there any difference? No. When you multiply numbers, you can change the order. When you multiply vectors, sometimes you can't change the order. Or if you do, you get a different answer. So that's going to be something that's different. It's going to be an example where you multiply and you don't get the same answer. You might see that on, won't see it till Thursday. All right, so the commutative property, I'll draw it out and show you. If you write what's in the box, that's all you really need. It's going to be kind of hard to do what I'm doing on the smartboard in your notes because I'm going to move things around. All right, so the commutative property says that if you change the order, you get the same answer. Okay, let's do what's on the left first. That's V plus W. Okay, so I'm going to connect it. And I'm not using a grid, I'm not using a ruler, so it's not going to be perfect, but it's going to be close. Okay, any questions on how I just did V plus W? Okay, now I'm going to take W and put V on the end of it. Okay, it's different than the way I added before. Draw my arrow, and if I put it up, again, I didn't use a ruler, but they're the same. Okay? Any questions on that? So vector addition is commutative. It's also associative. Okay, I'm not going to do this one out because it takes a little longer, but you could do exactly the same idea that I just did up above. With associative, you're not changing the order. It's ABC, ABC on each side. You're changing the grouping. On the left, you're going to add A plus B first. On the right, it's B plus C. Okay, but with vectors, it just works out very similar to how it would with numbers in this case. The associative property works. Okay, any questions on that? And again, A, B, and C there should all look bold. Okay, those are all vectors. What's the difference between vector V and vector negative V?
One's negative and one's positive.
So what would that mean if
One's
you drew it?
one's going one way, one's going the other way.
Yes, they point in opposite directions. So the direction is opposite, but what's the same?
The magnitude.
The magnitude. So keep that idea in mind. We just said that if you put a negative in front of a vector, it changes the direction. Keep that in mind. So we already did this kind of thing earlier. I'm going to come back to this. This equation is technically wrong. I want to see if somebody can figure out the mistake I have there. But if you add a vector to its opposite, you get the zero vector. What do I have to fix in my equation there? That does not say a vector plus its opposite equals the zero vector. You have to fix something. But Kim, do you know what I have to fix?
You just get rid of the addition symbol.
Well, I still want to say a vector plus its opposite. So I still want to represent adding two vectors, but that's not what it equals. Yeah.
Put an arrow.
Right. I'm saying that a vector plus its opposite is the number 0. No. It's the vector 0, not the number 0. Or you could have made it bold. Either way. Okay, but again, keep that in mind. A negative in front of a vector just means to change the direction, rotate 180. So why is that important? because of this. If you can add two vectors, you should be able to subtract them. We already know how to do addition. So let's pretend that I just gave you a subtraction problem with numbers. And you wanted to explain to somebody how to do subtraction, and they don't know subtraction, but they understand addition. How could you write 3 minus 2 as an addition problem? Yep, exactly. 3 plus the opposite of 2. 3 plus the opposite of 2. Well, that's all we have to do if we want to subtract two vectors. Instead of writing it as a subtraction problem, we're going to do it as addition. We're going to add the opposite. We just have to keep in mind what opposite means when we're talking about a vector. So Ezekiel, what did we just say that when you put a negative in front of a vector, what does that do to it? Reverses the direction. So to subtract two vectors, all we're going to do is take the second one, we're going to flip it around and add it. That's how we do subtraction. Before we go through an example, any questions on the idea? So we're going to take the second vector, we're going to flip it around, and then we're going to do addition just like we always do. Okay, so let's try v minus w. First thing is I just want to think of v minus w a different way. I want to think of it as addition. So Casey, kind of using the idea that we just had, how can you rewrite v minus w with addition?
V plus negative w.
Right, we're going to take v plus negative w. So the two things we're going to add are v and negative w. Well, I've got v. I need negative w. So for me on the smartboard, it's really easy to just flip it around. I don't have a thing that says rotate 180, but what I can do is I can flip it left, right, and then I can flip it up, down. And now it points exactly the opposite way. If you want, you know what, I can leave the original. And I'll do it separate. That was the original. Flip left, right. Now I have negative w, and now just add them together. Take v plus negative w, and again, what I'm really doing is subtraction. And that's it. That's the answer.
That's the answer?
Yep.
That's the answer.
V plus negative w. Any questions on how we did subtraction?
So the red line is the answer.
The red line is the answer. You can leave the red line right there if you want. I just moved it apart so you can see it separate.
Wait, so basically
What do you
it's
use
the
this
opposite
for?
of W.
When you subtract, yes.
What are you gonna?
You find the opposite of the second one and add. Yep. Okay, next one, scalar multiplication. What does it mean to scale something?
Take all the scales off.
Like when you like a fish or something? Okay, so that is maybe one meaning for scale. How about another meaning for scale?
A ratio. Like scale. Put it on the scale. Take a step on the scale, see how much you weigh. Stop.
Just stop.
You guys
Like
have
when
a
you're
scale
just embarrassing yourself.
Well, when you step on a scale, I don't think you're saying you're scaling yourself. I think you're weighing yourself.
Yeah, you're already gonna stop, alright.
So, it's a good try. But what about like scaling like in drafting or like blueprints, like if they said it's to scale, like, or like model cars, things like that.
I said ratio.
It's kind of like you're changing the size based on like an exponent.
So you're changing the size based off of a number. It's a scale factor. Some things you might scale larger, like in science you might make a model of a cell. Cells are very small. You might draw a larger version of it. So you've increased the scale. If you're doing blueprints, you're probably not going to make the blueprint the real size of the house, be a little big. So you scale it down. 1 inch equals 1 foot is a common scale for a blueprint. But the point is it's a larger or smaller version. So when we scale a vector, that's basically what can happen. We can take the vector and make it longer, or make it shorter. If you multiply by a number bigger than 1, it gets longer. Multiply by a fraction, between 0 and 1, it gets smaller. So a scalar, that's the number that you multiply by. So for example here, the scalar is 3. I'm taking vector v and scaling it up by a factor of 3. Now, what would happen if I multiply by a negative scalar? I kind of just talked about that. It would change the direction. So a scalar can do 3 things. It can lengthen, shorten, or it can reverse the direction. Okay, any questions on that? All right, so we'll look at a couple examples, and again, the answer to these problems is going to be another sketch. We're not doing sketches all week. Okay? In fact, we'll finish sketches pretty much tonight. Okay, let's look at 2v. And 1/2 v. How would 2v compare to v? Double the magnitude, double the direction, double the length, yes. Double the direction, that doesn't make sense. So, easiest way to do that is just to take a v and then put another copy of it. And there's the answer. Just draw it as one arrow. So direction stayed exactly the same. Magnitude as a speed, twice as fast. As a force, twice as strong. Of a pull or a push or whatever you're doing. 1/2 v. There's no easy way for me to draw something a half unless I measure it. I'm just going to kind of estimate it. And say, maybe even a little shorter. That's about 1/2 v. Okay, so any question on finding a scalar product? Yep.
That's kind of a problem. They'll give you the original V to figure out what V2 what it look like and 1/2 V look like.
Yes. Yep. Other thing I want to make sure we understand here is, what is that thing I just circled again? It's the scalar. The number in front is called a scalar, but it's just a number. Okay? So whenever you do a scalar product, it's a number times a vector. That is not a vector times a vector. Vector times a vector, that's going to come on Wednesday. We just did a number times a vector. So any questions what a scalar product is or how to do it? All right. All right, let's try this one. So negative v. In the other class from last week, somebody had asked me, well, what's the difference between negative 1v and negative v? There's no difference. Just like with variables, if you want to put the 1 in front, it's fine. If you want to write it like this, it's the same. So Michael, how would I sketch negative v?
It would be, reverse it, reverse regular V.
Yep, it's from regular v. What would you do?
Reverse it, right?
Yeah, just reverse the direction. So just go like this. I'm not going to take time to do it perfect, but that's the idea. Okay, and negative 1/3 v. To get negative 1/3 v, not only do I reverse the direction, but I also do what else? Yeah.
Cut it down to a third.
Yeah, make it a third as long. So I'm just going to kind of estimate what I think a third is. Bless you. Okay, any questions on that? All right, let's just do that one. So now we're combining addition and scalar products. We have 2v minus w plus u. I don't have everything I need to do that. What am I missing that I'm going to need to find first? Well, I can find 2v just by stacking 2v's together, so that's okay. But yeah, we do need to find 2v, but I have the material to find it. There's something right now I don't have the building block for. I don't have negative w. Okay? I need to create that from w. So we'll just take w and have it point the other way. Now I have all the pieces I need to stack together. But I need to kind of look at where I'm going to go to get an idea where should I start. So v is up and to the right, w is down and to the right, oh, I'm sorry, negative w is up and to the left, and u is up and to the right. So why don't we start kind of in the middle, but more towards the left side. All right, so we'll start about there. So there's v. I'm going to put another v. There's 2v. And all of the arrows should make a path. You should never have a collision. Okay? You shouldn't have a situation like that, where two arrowheads are colliding. They should all form like a path. Now we need minus w. So I'll take that. And plus u. Put that on the end. Okay, so I've stacked together everything. How do I get my final answer? Caitlin?
First arrow.
Yep.
The last one.
So the initial point of the first arrow to the terminal point of the last one. And it's about as straight as I can do it. And that's the answer. So any questions on that? All right. Okay, so this symbol, when you see double bars around a letter, double bars around a letter that represents a vector, that symbol means magnitude. The magnitude is the length of the arrow. So, if the magnitude is a length, what kind of number is length always? Yeah?
It's horizontal.
A horizontal number? I'm not sure.
Like a mountain on a graph.
Well, the vector could be going up and down. It could be vertical, it could be horizontal. But when we measure the length of it, length can only be a certain kind of number. It can only be positive. Okay, you can never have negative magnitude. You can measure the distance the other way, but that's not negative. If you measure the distance from here to Boston and Boston to here, it's the same distance, assuming you could fly. You might have to take different roads if you had one-way streets or something like that. But assuming you could fly, same distance. positive. So what would be the difference between the magnitude of v and the magnitude of negative v? Ian? Nothing. There is no difference. Those are the same thing. Get back to my example with Boston. That's like measuring the distance from here to Boston, get that number, and then measure it the other way, Boston to here. It's the same distance. It's the same thing. Now, if the length of a vector does come out to exactly 1, that's called a unit vector. Just like when we did trigonometry on a circle with a radius of 1, we called it a unit circle. If your vector comes out to exactly 1 unit, it's called a unit vector. So there's a lot of vocabulary in this section. Terminal point, initial point, unit vector, magnitude, direction. But once we get through the first part, there's much less vocabulary the rest of the week. Okay, so any questions on what a unit vector is? All right. All right, so now we're going to start to get away from sketching. If we have a word problem, we'll go back to it. Sketching is great for word problems. But if we want to add and scale and subtract vectors, eventually I want to show you a way to do it with just numbers. So if we're going to use numbers, we've got to have a way to represent vectors besides arrows. There's 2 ways to do it. This way is not as common, but it's the first way I'm going to show you. And it's the only way I'm going to show you today. Your book calls this an algebraic vector. It looks kind of like a coordinate, but instead of parentheses, it has these angle brackets. In physics, have you done anything with that to write vectors? No? Have you used like I and J, those letters, I, J, K?
We don't really do anything. I don't think
You don't do it, no?
I don't. He doesn't teach us a lot.
It just goes over homework.
Can you go up a tiny bit for 1 second?
So think of A and B as components. They're basically directions. So starting from somewhere, A tells you which way to go and how far to go, left and right. B tells you which way to go and how far to go, up and down. So again, just saying what I just said, writing it out. If it doesn't make sense still, you can write this down. But if you kind of understand what I said, you're probably okay. So you start at some point, okay, wherever you want. Just pick a starting point. Let's kind of do one as we go. So I've got the vector 2, 3. Okay, I'm going to pick a starting point. Anywhere you want. A tells me how far left or right to go. So in my problem, this is A, that's B. A is 2. So from the initial point, I'm going to go 2 units right. I'm not going to put a dot yet because that's not the final answer. And then B tells me how far to go up or down. B is 3. I'm going to go up 3. 1, 2, 3. I just drew a picture of the vector 2, 3. So think of those as directions from the initial to the terminal. Or you could start anywhere you want. I could take this, let's make a copy of it, and see if I can just move it over there. That's also the vector 2, 3. You can start anywhere, but where do you think the most common place to start is? The origin. So this notation doesn't tell you where to put it. I already said that. It doesn't tell you the position. You can position it anywhere you want. But if it does start at the origin, it's called a position vector. So if a vector starts at the origin, it's called a position vector. Have you mentioned that word at all in physics, position vectors? Yeah. Okay, so the last thing I'm going to do is show you how to find a position vector. Okay, but I need to make the right-hand side, I need it bigger to work with. Okay, so I could put it in any quadrant, but what I'm going to do is I'm going to put it in quadrant 1 because it makes the numbers easier to work with. I'll just move the whole grid. Just keep that one. Okay, everyone good on the left so I can make the right side bigger? All right. So, what I need to do is write the coordinates of these 2 points. Okay, let's start with the initial point. Matt, what's the coordinates of my initial point?
3, 3.
Yep, 3, 3. And what's the coordinates of my terminal point?
5, 6.
5, 6. Yeah, it's 5, 6. Now, we already know what the answer is supposed to be. It's supposed to be 2, 3. That's the answer. What can you do with these 2 coordinates to get that as an answer?
Subtract the initial.
Subtract them, yes. Take terminal minus initial. 6 minus 3 gives me 3. 5 minus 3 gives me 2. That's all you have to do to find a position vector. And that's the last formula I'm going to give you right now. So, to find a position vector, you're going to be given 2 points, 2 coordinates. We'll call them P1 and P2. If you come across a problem and it doesn't tell you which one is initial and terminal, assume P1 is initial, P2 is terminal. To get the position vector, you're going to subtract. And the order is important. Terminal minus initial for the x's, terminal minus initial for the y's. And that's what you guys just did on the other page. Okay, so we'll finish up. I'll give you one more example of, I'll give you 2 coordinates, and I'll just ask you what is the position vector. Make sure when you write your answer as a vector, do not put parentheses. Parentheses are coordinates. Okay? Vectors are not coordinates. Okay, let's try that. So find the position vector. It doesn't say which one is initial and terminal. So how did I say to determine it if they don't tell you? Kelvin? How do you know which one is initial and which one's terminal?
First one.
Yeah, P1. The 1 is initial, 2 is second. That comes after terminal. So AJ, what's going to be my calculation for the x complement?
4 minus 1.
4
So 4.
minus 1, which will be 4 plus 1. And my calculation for the y component, Dave?
Yeah, space now is just
Well, look at the formula. The formula is y2 minus y1.
-2.
What's y2?
Oh. Oh. Never mind. -6.
y2 is 6.
What do we get?
What's y1?
I was doing y1 first. It's 2.
2. 6 minus 2. Hannah?
4.
Gives us 4.
They saw it. I saw it.
Right, so if you wanted to sketch that vector, and you wanted to start at the origin, put your initial point at the origin, put your terminal point, right 5, up 4. Any question on how to find a position vector? All right. Okay, so homework tonight it's on 344. Remember, it's not in the book, it's in the packet, which I'll try to put the packet at the end of the video. But it's 1 through 10 all, 14 to 22 even, and 26 to 32 even. On 26 to 32, do not follow the directions they have there, just find the position vector.